Next up, we have Xuyang, who will tell you all about the Cairo resource machine. You just heard about the RISC-0 protocol adapter resource machine, but as you'll soon discover, the resource machine train never ends. Xuyang.
Hello, everyone. I'm Xuyang, and today I'll present the Cairo resource machine. I'll walk you through the basic transaction workflow, and I also will dive into technical details, especially the decision we made for Cairo resource machine and shielded resource machine. Okay, Cairo resource machine is actually a shielded resource machine instance built on the Cairo ZK VM, where we are using the underlying zero-knowledge proof for compliance and logic proofs based on the ZK Stark system. And it starts from the Juvis Cairo front end provided by our Juvis team, and it ends up with the Anoma Cairo resource machine backend. All the things are available in our repo. Okay, let's start by the transaction workflow. First, the user needs to fetch the ciphertext and Merkle path from the service. Once they retrieve the encrypted resource and do the child decryption, and then they can figure out the resources belong to them, and then with the resources, they can further obtain the Merkle path to prove the resource existence from the cloud service, and then we already get the user already got all the data for the proofs, and then they also need the logic, right? We can, the users can use the Juvis language to write some logic programs. Then use the Juvis Cairo compiler to compile down the logic into proving key and verifying keys. Yes, for the users is that. Then let's move to the next step. For specific applications, users can compose or create some actions based on the data and the logic they already own. Generate the compliance proof, logic proof for each action, and then construct the initial transaction. Never mind, I'll introduce the details about the actions and transactions. I will not present the solving, the ordering, and the consensus protocol. They are out of scope for this presentation. So once the initial transaction is finalized or is solved, we can get a balanced transaction. Then we can generate a delta proof. That means we can submit the transaction to the Anoma node. The last step, when the Anoma node receives some transactions from user or solvers, Anoma node validate the transaction. If the transaction is valid, update the state, namely update the commitment Merkle tree, maintain the Merkle root history, update the nullifier set, and store all the ciphertexts. That's the basic procession of the transaction. Then let's dive into the technical details. It's a standard resource struct. I'm not going to go over all the elements listed here. I'll just introduce some properties that are essential for Cairo resource machine or for shielded resource machines, like the logic reference. The logic reference indicates the hash of the predicate logic. Actually, it's a hash of verifying key. It is decided by the resource machine. Users cannot modify the logic reference hash. But for the label reference and the value reference, users or the developers can encode arbitrary data to the label and the value. And we recommend using the Poseidon hash to do the encoding, which would make the circuit more efficient. The quantity, eventually the quantity field will be converted to a finite field. So we also need a range check here to make it secure. Next is the ephemeral flag, which is a rule. It's a key element to achieve the intent. Intent resource is a special resource with a true ephemeral flag. And for the privacy consideration, we don't want to expose the ephemeral flag of resources. It means ephemeral resources and non-ephemeral resources are distinguishable. Later, I'll introduce the details. And here, and next, we also have the nonce to ensure the resource uniqueness. We also have the special constraints over the nonce to make it unique and to avoid maliciously set the nonce to create some duplicate resources. The last one is the random seed. Random seed is an important field for shielded resources. We need the random seed to derive some blunt factor to protect the resource commitment and resource nullifier. Then let's move to action. The action includes two main parts: compliance unit proofs and resource logic proofs. The compliance unit contains one consumed resource and one created resource. We want to make this more because it's good for parallelization and proof aggregation. Let's take a look at the witnesses and instances and the constraints in compliance unit proof. Overall, compliance unit proves that one resource is consumed correctly and one resource is created correctly. So the first constraint here is to check the nullifier integrity and the Merkle path validity. It corresponds to the witnesses of the first line and the instances of the first line. The Merkle path, we have the Merkle path to prove the existence of the consumed resource. And we also need the consumed logic reference in the instances because we need to further check the correspondence between compliance unit and logic later. For the created resource, we only need to check the commitment integrity. And the last constraint here is the data integrity. Data proof. Data is the key element to prove the balance of a transaction. We'll talk about the data proof in transaction section. Just remember all the elements here, because each element is valuable for the next for the next checks. Okay, let's take a look at how to make sure how to prove the existence of consumed resource. We don't want to expose which resource is consumed, so we check the root existence instead. There are some checks here to make the ephemeral and non-ephemeral resources indistinguishable. Like for ephemeral resource, the ephemeral resource will be consumed and created in one transaction. So ephemeral resource have a very short lifetime. So we cannot provide existence proof for ephemeral resource. And we also want to prove the indistinguishability of them. So the Merkle path, we provide a valid Merkle path and root validation for non-ephemeral resources. And we just provide a dummy Merkle path and an existed root for ephemeral resources, so that from public or validators' perspective, they cannot distinguish ephemeral and non-ephemeral resources. As we know, the nonce ensures the uniqueness, but a duplicate resource can also be created via malicious nonce setup, right? Trivial solution is to check the duplication every time when we want to insert a new resource to the Merkle tree. That's not what we want, right? We already have a proof. We want the proof provide as many constraints as the proof can. So we use the consumed resource nullifier as the nonce for the new created resource to make it happen. As we know, the nullifier is unique, so the nonce is unique. So we can make the created resource unique. Then we can go to the logic proof. The logic proof is a deterministic application program written in JUVIX. It checks the context integrity, or the current resource integrity, and the existence of the current resource. It also includes verifiable encryption to make sure the receiver can decrypt resource. And there are other additional constraints decided by specific applications. Okay, let's talk about the verifiable encryption in logic proof. Why do we need verifiable encryption? In general, there are two kinds of encryption in blockchain, like out-of-band encryption and inbound encryption. Um, Out-of-band encryption means that sender and the receiver need to create a security channel by themselves and share some secrets. That's not what we want. Inbound encryption means the sender is responsible to add the encryption to the transaction so that the receiver can decrypt it. But why verifiable here? In our MASP or Zcash project, inbound encryption is sufficient for them. But for us, especially when we introduce intent and involves multi-parties, things are different. Because, for example, we have three actors in one transaction. Alice creates encryption for Bob. Bob creates encryption for Carol. Carol creates encryption for Alice. It's a circle, right? Alice can maliciously gives out wrong encryption to Bob without sacrificing her own benefits, because Carol will may create a good encryption for Alice. The verifiable encryption here is a typical hybrid encryption scheme. We use the David-Hillman key exchange to generate a symmetric key, and we use the symmetric scheme to encrypt the plain text. So, because it's verifiable, so the receiver with the cracked secret key can definitely decrypt the ciphertext. To make the encryption efficient, we are using the Poseidon-based symmetric encryption in Cairo circuit. After introducing the compliance and the logic proofs, we also need to check the correspondence between compliance and the logic. First is the logic reference correspondence. We already proved resources are created and consumed in compliance proofs. We also need to make sure correct logic execution or correct logic proof generation. If you remember, we have the yes, we have the logic reference in the instance of compliance unit. The resource machine would dereference the resource logic to get the verifying key to make sure the expected logic proof will be verified. If we want to achieve function privacy, here should be a logic commitment instead, because we don't want to expose the logic information. And then we also need to guarantee the logic context correspondence. It is basically a problem of context sharing between different proofs. As the as the circuits have a deterministic constraints, so the circuits don't support a variable number of reading in inside. So we build a Merkle tree to share the context between compliance and logic proofs. That's all for the action. Then we can move to the transaction. The transaction contains a bunch of actions and a data proof. The data proofs ensures the balance and the integrity of shielded transaction. We can take a look at the data structure, which is constrained in compliance unit. We can get the data from the compliance unit instance. The R resource in is the consumed resource quantity multiply consumed resource kind. The kind is derived from resource logic and the resource label, which is unique. This part is for created resource. Here we also need a blend factor to protect the privacy of the data. If and only if it's a balanced transaction, we can generate a data proof, namely a binding signature. From this equation, we can find out if it is balanced, the sum of the compliance unit data, like this part, will be eliminated. It's a sum of these parts, and the private key would be the sum of the blend factor. It's exactly a key pair for signature, so we can create a standard ECDSA signature for the transaction. That explains why only a balanced transaction could have a data proof here. Our next step, as mentioned, we still need to do the child decryption for the ciphertext. In next session, Yulia and Enric will introduce a new technology, shielded state sync, would make the child decryption easier. And there are many proofs in the transactions in actions, so the proof aggregation would significantly improve the efficiency. And we also want to protect the privacy of logic. So we already have a framework for function privacy. I hope next time we can share more details about the function of privacy. And I also will show you some examples we have in our repo. It's a standard Cairo compliance circuit written in Juvix. It proves the integrity of commitment, non-fair, and the data is quite neat and concise. Thanks to Juvix team's work to make it happen. We can also take a look at the witnesses we need for the compliance proof. Input resource, output resource, non-fair key, and the Merkle path. Users and developers don't need to worry about the structure, because the resource machine will generate the JSON format automatically for you. We also provide a powerful Juvix Cairo library for developers. Here we can take a look at the logic example. Like we load the self resource, non-fair key, and the Merkle path under the verifiable encryption. It's also very easy for developers to create a resource logic in Juvix program. Yeah, I think that's all I have today. Hope you enjoyed. Let's see if we have some questions.
All right, thank you, Xuyang. Do we have questions from the live studio audience? Keep them concise, Michael.
Thank you for your presentation. You mentioned proof aggregation as a possible way to lower the costs. In which part would you then start with aggregating proof, and where would it be the easiest?
I think the compliance proof aggregation would be the easiest way, because the compliance circuit is a fixed one. We can easily aggregate the compliance proofs. The logic proofs are different based on different applications. We may have some problems, but it can be solved. Yeah.
I have a very basic question. Given that you have a Cairo implementation, but also a RISC-0 implementation, does this imply that you can just basically have any kind of proving backend that you want with the resource machine?
Yes, exactly.
Modulo engineering details. Any other questions from the live studio audience? All right, then we have one question from the internet, which is when testnet. I will take this one. So we have something currently live that we are calling a DevNet, as in it's intended for developers, and it is really early stage. There are already some great docs on the DevNet at docs.anoma.net, and you can find the code, for example, which Xuyang just referenced, is fully open source, so you can look through it and start playing with it. Developers, beware, this is early frontier territory, and there may be great beasts lurking in the wilderness, but also lots of interesting things to check out and play with. So try that out, let us know what you think. And of course, further test nets that are perhaps a bit more user accessible will follow later this spring and throughout the year.